Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 11. We have been discussing about the equilibrium phase diagrams, and particularly I had mentioned about the case when two materials, although fully soluble in liquid, may have a problem while going into solid phase, and they may not be fully soluble in the solid phase. So, in context of that, we started doing the iron carbon equilibrium diagram, where this property of carbon going up to a maximum of about 6.67% in the solid phase remains or prevails, and this would be a very interesting example of a good equilibrium phase diagram. So, let me just sort of reiterate what I had done in this diagram. This right here is the iron carbon equilibrium diagram. You can see that beyond 6.67% is 100% ferritic stage which comes, and we cannot load beyond this. And there are many phases of this diagram. For example, the phase that can be used for mostly casting processes are in this range of 11-25 degrees Celsius, which corresponds to more than 2% carbon. Okay, it is about 4.3% at this time, you can see here, and still it is in liquid form in this particular region. So, then there is a region which is important for heat treatment of steels, which is 723 degrees Celsius, which is this particular region right here, and this is related to the sort of metal working processes. It can be metal forming of various kind. So these are some of the temperatures which are used, and also 723 degrees is very critical because you can change the properties of the material at this particular temperature by heating, cooling, and doing various kind of heating, cooling, and all sort of chemical treatments or heat treatment processes like carburizing, nitriding, so on and so forth. So this temperature is very critical from a materials properties standpoint. There are there is yet another region which is actually important from the materials engineering point of view, which is this region right about here, where there is a phase delta iron again, which is an allotrope, allotrope of iron. As you are already aware that there are three different states or crystal structures in which iron can be present. One is below 910 degrees, which actually forms the alpha iron phase, which has a body centered cubic structure. The moment you go above 910 all the way to about, let us say, 1400 degrees Celsius, you have the gamma iron, the austenite, which is actually the face centered cubic structure, and then the delta again becomes the BCC. So basically it is a transition from BCC to FCC to again BCC, which happens, and then this delta iron BCC is always above 1400 degrees Celsius. If you may just remember from the last lecture, we had discussed this, where we had made clear how this iron changes states or crystal structures at different temperature ranges. So this is also a very important zone, particularly this zone here from a materials engineering standpoint, although in the applicative standpoint it may not be much used, because at such a high temperature metal is seldom used for any of the practical applications. So the two zones of this curve which are really important from an application standpoint are this zone right about here 1125 degrees, and this zone which is about 723 degrees Celsius. So there are other type of transformations similar to the eutectic transformations. We had discussed eutectic, if you remember, in the last lecture, where in the eutectic case, in the eutectic transformation, a single phase liquid changes to a two phase solid. if you may remember in the ice salt diagram, we had talked about salt water which was completely uniform homogenized and it gets freezed below minus 22 degrees Celsius at a certain percentage of salt, and that structure, although it is not distinguishable, but it is a two phase. So, basically salt is entrapped homogeneously within the ice crystals. Okay. So, that is what eutectic transformation is. Here also the similar kind of a behavior can be observed, and here really the eutectic transformation point could be this point E right here, where we have a conversion of the liquid into homogeneously available two phase solid structure, which has gamma iron, which is the FCC iron, and Fe3C cementite. So cementite is dispersed uniformly across the gamma iron phase. So, there is nothing called excess cementite or something like that, it is all one structure that is there. Okay. And so, this is how you can actually change the process and make a one phase, a single phase liquid completely convert into two phase solid. Okay. Two phase solid meaning that you have the presence of both the phases throughout the particular crystal. The other point which is interesting for us to consider is the eutectoid. Okay. And the eutectoid transformation in this diagram corresponds to a situation where instead of a single phase liquid, a single phase solid changes into a two phase solid. Okay. So, in this diagram, if we look at carefully this particular point E dash right here, we have on one hand gamma austenite, which is a complete FCC. So, in this case, as you know, the austenite is already a FCC structure, and then you are going to convert that into perlite, which is again a a sort of again a two phase solid structure of. So, it is a combination of cementite and ferrite being the alpha iron, which we commonly know as the BCC crystal, and cementite is Fe3C. So, basically again it is another case where the solid that is formulated has a continuous distribution of both the alpha as well as the cementite, the ferrite as well as the cementite all through the crystal. Okay. So, similar to the composition what is here a two phase solid, similar kind of a composition exists in this particular region, and this is known as perlite. Okay. So, that is the eutectoid point. So, these two transformations are very important from the standpoint of the application application in the industry. But the materials engineering property, as I told you, comes in this phase, where there is another transformation which is actually known as peritectic transformation, and I will just define what peritectic transformation means. So, this peritectic transformation refers to a point of is done at a temperature above which all the liquid solidifies and the atoms diffuse into the already existing solid forming a single phase solid. If we look at this point right about here, you have a single phase solid delta in this region over it, right. So, this is the delta iron, and you have delta and liquid in this particular region, which is showed by this. So, you have semi solid, semi liquid kind of a transition here. Now, if I look at the structure which is just about here, it is a combination of the delta and the gamma iron. You remember delta is the BCC phase and gamma is the FCC phase. So, both of them are combined here, and the moment it is changing the temperature, it is going into a single phase solid, that is delta plus liquid. So, whatever is happening to the gamma structure, it is sort of reorienting itself towards the BCC from the FCC structure. Okay. So, you are formulating a single phase solid above this temperature, and below this temperature it is always a two phase solid. So, basically from a two phase solid to a single phase solid in terms of the structure is converted when we talk about the peritectic point. So, this is of not much significance although, but they from materials standpoint or from engineering standpoint, material engineering standpoint, we try to explore this particular point of temperature. So, having said that, we have these three eutectic, eutectoid and peritectic points in the iron carbon equilibrium diagram. So, let us see structurally again. So, at 1125 degrees Celsius, the solubility of cementite in gamma iron is limited to 2%. You can see this right about here in this curve. 1125 degrees Celsius is this temperature right now, and you can see that beyond 2% carbon, which obviously formulates Fe3C or cementite, the phase changes from gamma into gamma plus liquid. Okay. So, any further rise would lead to change the phase and cementite would start coming out. Okay. So, maximum 2% can be held, and that is where the steel zone really is. Beyond this, it starts becoming more like cast iron. The solid solution of gamma iron and Fe3C is commonly known as austenite, which is actually right here. Okay. This gamma iron and Fe3C, these are the austenite. In the BCC phase of iron, the solubility of Fe3C is much smaller, around 0.33%, as you can see here. This is the BCC phase of the iron, right. So, we call it ferrite. Okay. And the moment the percentage increases to anywhere more than 0.33% carbon, again the perlite starts coming out. Okay. As you can see, this particular zone is ferrite and perlite, and if it goes beyond a certain point, 0.83, it again starts formulating cementite and perlite rather than ferrite and perlite. Perlite, remember, is the eutectoid single phase, two phase system of ferrite and cementite distributed throughout the structure homogeneously. Okay. So, if I look at the structures here, this is how the perlite would look like. So, it is a one uniform homogeneity, the mixture of ferrite and cementite. On the other hand, if you look at how the mixture of ferrite and perlite can be. So, there are some additional, you can see these white marks here, although these are not the actual structures, but it is just a cartoon indicative of what is going on. So, you have the pure zones of ferrite, apart from the perlite regions, which are the two phase solid, which we are talking about. And in this particular, you have the pure zones, the black zones are the pure zones of cementite, which are over and above the perlite, which is again a combination of, it is a two phase solid of ferrite and cementite. So, this is how you understand the iron carbon equilibrium diagram. So, the solid solution of Fe3C in alpha iron is called as ferrite. So, you have the ferrite in this particular region. The eutectoid composition of ferrite and cementite is perlite. Again, you have this perlite here, which consists of alternate thin laminates of cementite and ferrite. So, that is what I am saying, that the two phase solid you must always demarcate as one where structurally there is no difference. The presence of both the phases are equal throughout the crystal matrix. Okay. There is no separate zone for the presence of one over the other. So, that is how a eutectoid or a eutectic composition would typically happen. Okay. But then anywhere between the before or beyond the eutectic or eutectoid composition, which are also known as the hypoeutectic, hypoeutectoid, as well as hypereutectic, hypereutectoid composition, you always have this tendency of one phase coming out and becoming independent. In this case, you can see, for example, the ferrite phase came out. In this case, you saw the cementite phase came out. So, there are pure zones of this cementite or ferrite formulated over and above the uniform two phase solid structure perlite which is there. Okay. So, that is how you basically try to understand the iron carbon equilibrium diagram, and the different structures of various phases of steels are kind of indicated here. You have this ferrite austenite, you have this austenite which is again a two phase solid combining, but then Fe3C is homogeneously distributed around the matrix. Then you have a cementite and austenite combination, okay, which happens over this temperature in this particular region. So, the structure of ferrite is thick and rounded, whereas that of cementite is thin and needle like. These are some of the properties. Ferrite is soft, cementite is very hard. The transformation of austenite into ferrite and cementite is achieved only when the cooling is slow. So, that is a very, very important factor as well, and we are going to do the time temperature transformation diagrams very soon after this, which we talk, where we talk about the impact of cooling into the various structures. So, if a rapid cooling rate is, for example, provided to let us say austenite, it may transform into altogether different phase martensite. Okay. So, the rate at which the cooling happens is also going to enable what is the final structure that gets formulated, because you are not giving it enough equilibrating time, and obviously the diffusion processes are quite slow. So, there are going to be some changes in the crystal based on that. So, having said that, that is how you study this equilibrium phase diagram of very important iron and carbon, and this is used very commonly in the industry. It is a one snapshot go of what phase, what temperature, what percentage, what let us say structure gets formulated. So, you can have visualized all these things in a single sheet of paper through this diagram. So, having said that, we want to sort of close on to this module, but then in the next module I am going to do some things related to the control of material property, where the cooling rates become very, very important, and we will talk about a diagram which is famously known as the TTT, or time temperature transformation diagram. With this I close the module. Thank you so much.